Welcome back, everybody. This is our first class in JEE Mains previous year questions for class 12th for the chapter Dual Nature of Matter and Radiation. And previously, we have made several videos in this series, and all of those videos are available on our YouTube channel's playlist section. We have also started similar series for NEET. So if some of your friends are preparing for NEET, then you can guide them through those videos. And if you find these videos useful, then do press the like button, share them, subscribe to our channel. Also, if you are like to support us, then scan these QR codes and support us financially. It will be a great help. With this, let's start today's video. Now, starting with the question 1. Here, an electron is doubly ionized helium positive. Let me adjust thickness first, band thickness. And a proton are having same kinetic energy. The relation between their respective de Broglie wavelengths. So we know that de Broglie wavelength, that is lambda, is equal to h by p. Now, it is mentioned that they have the same kinetic energy. So this momentum P can be written in terms of kinetic energy, so that it can be written as under root 2m E, where E is the kinetic energy here. So from this we can write, we can see easily that H is constant here, twice is constant here, means same for both, and energy is also same for both. So from that I can write that lambda is inversely proportional to under root of m. So if I now divide wavelength for electron, He positive and proton. So let's first do let's start with these two. So lambda electron by lambda of He positive will be equal to under root of mass of electron divided by mass of He positive. Now we know that mass of He positive is very large as compared to the mass of electron, because normally approximately mass of electron is mass of proton or mass of neutron divided by 1868, and mass of helium positive will be approximately 4 times mass of proton. So basically this whole number will be greater than 1. So from this we can write L lambda E divided by lambda of He positive will be greater than 1. So from this, lambda of electron will be greater than lambda of helium positive. And from that, option first satisfy this relation, means this is, and option C is also satisfying this relation. Option B and D does not satisfy this relation. So both of these are cancelled. Now writing same for the helium and proton, what we will get? He positive by proton, that will be mass of He positive by mass of proton. Now this will give us 1 by 4, because mass of helium is 4 times mass of proton. So lambda He positive by lambda proton will give us under root, after solving for under root we will get half, and this will lead us to that lambda of proton is equal to twice of lambda He positive. So from this we can say that lambda of proton is greater than lambda of He positive, and we already concluded that lambda of electron will be way higher as compared to the lambda of helium. So basically we will have relation lambda E is the greatest, then comes the lambda proton, and then comes the lambda He positive, and that is our option C. So option C is going to be the right answer here. Let's move to the next one. Assuming the nitrogen molecule is moving with the RMS velocity 400 Kelvin, means RMS velocity at 400 Kelvin, the de Broglie wavelength of the nitrogen molecule. So here first we have to calculate the velocity. From that we will find out momentum, and then we can find out the RMS velocity. We can say de Broglie wavelength. So Vrms here will be under root 3 kT by m, and that m will be small m. This will be the mass of one molecule of nitrogen. If we want in terms of molars, so that can be 3RT by capital M, where R is the Rydberg or gas constant and capital M is the mass of one mole, not mass of one molecule. So, and why we are taking in terms of one molecule? Because we have to calculate momentum for one molecule. And that how we will calculate? First, we will calculate the kinetic energy. Kinetic energy of the one molecule will be half mv Rms square, and we are taking this formula. So half small m into 3 kT by m, and from this we will get 3 by 2 of kT. This is the kinetic energy of one molecule. Now we have a relation between momentum and kinetic energy. That momentum is under root 2me. So this will become 2m into 3 by 2 kT. So 2 gets cancelled, and basically we have a relation as 3m kT. Now we can find out lambda. Lambda will be h by p, and that will be h by under root 3m kt. So h is given here 6.63 10 raised to power minus 34 divided by under root 3 into, now weight of one molecule is already given. So that is 4.64 10 raised to power minus 26 into K, that is Boltzmann constant 1.38 10 raised to power minus 23 into temperature in Kelvin, that is 400. Now when we solve this, what we will get? We will get 0.243 10 raised to power minus 10, and that will be 0.24 angstrom. That is option A for us. Now, even if the mass, molecular mass or weight is not given, then what we can do? We can use method that mass or weight, you can say weight of one mole, and this is nitrogen molecule, means we are dealing with N2, that will be equal to 14 grams for one mole. Now, in one mole, there will be Avogadro number of molecules, that will be 6.022 into 10 raised to power 23 is equal to 14 into 10 raised to power minus 3 grams. Oh, sorry, kilograms. 14 grams and 14 into 10 raised to power minus 3 kilograms. And here will be mass of one molecule. So small m will be 14 by 10 raised to power minus 3 divided by 6.022 10 raised to power 23. So that's how we can calculate if it is not mentioned in the question, right? Oh, sorry. Uh, it is 14 is the atomic weight. For N2 it will be 28. So this is correction here. So this will be 28. Now if we see, then we will find the value nearby to this value. So with this, let's move to next one. So let me first slide it slightly. Okay, now particle of mass m by 2 moving in x direction, x-axis with velocity v naught collide elastically with another particle at rest having m by 3 mass. If both particles move along the x-axis after the collision, the change delta lambda in the de Broglie wavelength of particle 8 in terms of de Broglie wavelength lambda node before collision. So we know that de Broglie wavelength, that is lambda node here, will be equal to h by the momentum and momentum of the first particle. So that will be Pa, let's say. So h by Pa will be mass of first particle m by 2 and its velocity is v naught. So it will be mv naught by 2, or basically twice h by mv naught. This is the lambda node before collision. Now as there is elastic collision, so what will be conserved? Momentum is conserved, kinetic energy is also conserved, and coefficient of restitution E will be 1. Now, suppose this is the first particle with mass m by 2. This is the second particle with mass m by 3. Its velocity is v by 2. Its velocity is 0. They collide with each other and then they start moving with some velocities. This is m by 2 and this is m by 3 mass. Suppose its velocity is v1, its velocity is v2. Then according to coefficient of restriction, which is 1 here, that will be equal to v2 minus v1 divided by v by 2 minus 0. So basically v2 minus v1 will be equal to v by 2, and from this v2 is equal to v by 2 plus v1. Now we can conserve momentum. So according to momentum conservation, we will get m by 2. Oh, sorry, I made a mistake. This is v node. This is v node. This will be v node, and this will be v node. Velocity, initial velocity is v node. So m by 2 into v naught, that is initial momentum, because this first second particle is at rest, will be equal to m by 2 into v1 plus m by 3 into v2. Now we have v2 relation in terms of v1, so this will become m by 2 v1 plus m by 3 v naught plus v1 is equal to m by 2 of v naught. So this will give us mv naught by 2 minus mv naught by 3 will be equal to m2 v1 plus mv1 by 3. So basically what we have, if we take LCM here and v node as common, but we will get 6, 3 mv node minus 2 mv node, so basically mv node, and here we will get LCM as 6, 3 mv node plus 3 mv1 plus 2 mv1, that is 5 mv1. So 6 gets cancelled, m gets cancelled, and v1 is equal to v naught by 5. This is the value of v1. Now let's calculate v2. So v2 will be v naught plus v1, that is v naught by 5. So that will be 5, oh sorry, 6 v naught by 5. Now we have to find out change in de Broglie wavelength after. So lambda dash, that is the wavelength of the first particle after collision, that will be h by the final momentum, that will be m times v1. So m v naught by 5, and delta lambda, that will be equal to, let's say, lambda dash minus lambda, and we take modulus to avoid the negative sign. So that will be 5h by mv node minus initial were 2h by mv node. So 2h by mv node, this will give us 3h by mv node. Now it has to be written in terms of lambda node, and our lambda node was 2h by mv node. So what I can do, I can write it like this, that 3 into 2h by mv node into 1 by 2. So this will be lambda node, so this becomes 3 by 2 of lambda node. Now if I check the possible answers, there it is. That is option A for us. Let us move to the next one. Question number 4. A particle is moving 5 times as fast as the electron. The ratio of de Broglie wavelength of the particle to the electron is given by this value, the mass of the particle. So we know that de Broglie wavelength is h by p, where p is the momentum. And from this, uh, we can write that suppose lambda of the particle divided by lambda of electron will be equal to momentum of the particle divided by the momentum of the electron. Now momentum of electron will be mass of electron, velocity of electron, momentum particle will be mass of particle into velocity of the particle. Now particle is moving 5 times as fast, means Vp by Ve is equal to 5. So lambda p by lambda e is equal to me by mp into 1 by 5 here. Now coming to the their ratio of de Broglie wavelength of the particle to the electron is given. So that is lambda e by, sorry, that is lambda e by p. Oh, I write it wrong. This is lambda p by lambda e basically. So lambda p by e is the ratio of the de Broglie wavelength for the particle to the electron that is given, and it is 1.878 10 to the power minus 4. Now mass of electron is 9.11 10 to the power minus 31 divided by, again this is mp, sorry for the mistake, and this is mp, and here we have 1 by 5. So basically from this, mass of the particle will be equal to 9.11 10 to the power minus 31 divided by 1.78 into 5. Now 18 into 5 is just approximately equal to 9. So what we can say, I can say cancel out this. And I forgot 10 to the power minus 3 here. So this will be approximately 1 into 10 to the power minus 27. And the nearby answer is, that is 1.2 into 10 raised to power minus 28. Means it might be something like 0.1 into, I think, no, sorry, not, it's, this is approximately. So if it is 1.2 into 10 raised to power minus 7, it can be like this, or it can be like this, 0.9 something into 10 raised to power minus 27. And this will not match with the option C, sorry. It will not match, but this can match. It can be written as 9 into 10 raised to power minus 28, and that is option D. So option D will be the right answer here. Now starting with the next one, a particle moving with kinetic energy E has a de Broglie wavelength lambda. If energy delta E added to its energy, the wavelength becomes lambda by 2. Then value of delta E is. So we know already that lambda, that is de Broglie wavelength, is equal to h by under root 2 m E. Now after addition of some energy, it becomes lambda by 2. So lambda by 2 will be equal to h by under root 2 m E plus delta. That will be the new wavelength. Now if I divide both of these, what we will get? I will get lambda divided by lambda by 2. H gets cancelled. And here I will have under 2m E plus delta E divided by under root 2m E. Under root 2m will also get cancelled, and squaring both sides we will get 4 is equal to E plus delta E divided by E, and from this we can easily find out that delta of E is equal to 3 times E. That is option C for us. Moving to the next one. An electron of mass m and magnitude of charge E initially at rest gets accelerated by constant electric field E. The rate of change of de Broglie wavelength for this electron at time t, ignoring relativistic effects. So we have to find out rate of change, means basically we have to find out d lambda by dt. That is the required value we want. So again, we know that lambda is equal to h by momentum, that is basically m into v. So we have and we know that velocity will depend upon time if there is acceleration. So from that we will get time dependence, and then we will take that. So here force acting will be q times e. From that, acceleration will be q e divided by m, and electron is initially at rest, so we can write that v is equal to 80, that is q e t by m. So from that, lambda becomes h by mv, that will give us q e t. Now if I take a derivative, then we will get d lambda by dt will be equal to minus h q e t square. So here they have taken charge in modulus. So I also have not still added the sign of charge. So it is q, and here q is actually minus of e, because charge is negative for electron. So a negative sign will stay as it is, and we have only one term which has the square in the denominator. So option D will be the right answer here. In the next one, electron of mass m with initial velocity given by this, electric field is this, lambda naught is the initial de Broglie wavelength of electron, that is de Broglie wavelength at the time t. So this is a type of question which I think we have already covered in NEET also. So if you have not watched those videos, you can also go through them. They will give you some additional practice also. So initial velocity is okay. This will not work. This only black is going good here. V node I plus V node J, and here electric field, and this is on electron. So force acting on electron will be minus E times the electric field, that is minus E node K. So basically that is E node K. So here force is along K direction. So from that, acceleration will also be E node by m along K direction. So its initial, you can say lambda node, initial de Broglie wavelength, that will be h by mv, and that will be h by m. And how we will calculate v? We will take modulus of this, and modulus of v will be here under v square plus v square, or 2v node square, and that will be root 2 times v node. So here we will get velocity s root 2 times v node, so that will be h by root 2 mv node. Now after certain time, there will be a z component added into the velocity. So velocity after time t will be equal to x and y component will stay as it is, v node I plus v node j, and there will be a z component that will be e node acceleration time t, so e node t by m of k. So that will be the velocity component, and in the z direction. So now if I take modulus, Vt modulus, what I will get? I will get V naught square plus V naught square plus E square, E naught square, T square by M square, and whole under root. Now this can be written like this, that it will be, if I take V node common, so here I will get 2 plus E square, E node square, T square by M square, V node square. Now lambda at any time t will be h by mvt. So this will be h divided by m. Vt is v node into under root of 2 plus e square, e node square, t square by m square, v node square. Now this term will, okay, I think we have to find out root 2 also, because we know root 2. Root 2 is also needed here. So what we have to do? We have to take this 2 also common. So out of under root it will become root 2, and this will become 1, and this will be divided by 2 here. So this will be 1 and root 2 here and 2 here. So this will become equal to lambda node. So this relation will look like this, lambda node divided by under root 1 plus E square, capital E square, T square by 2m square, V naught square. And that matches with option C here. Moving to the next, a particle P is formed due to completely inelastic collision of particle X and Y having de Broglie wavelength gamma X and gamma Y respectively. If X and Y are moving in the opposite direction, then de Broglie wavelength of P is. Now as we can see that we have a completely inelastic collision here. So we can say momentum will be conserved. So if momentum is conserved and both are moving in the opposite direction, so let's say velocity of x is vx, and velocity of y is vy. So here, and their masses are mx and my. So according to momentum conservation, mx vx minus m by vy. We assume that particle y is moving in opposite direction to the x. Particle x is moving in positive x direction, and particle y is moving in negative x direction. So that's why we take a negative m by vy. Now assume that after combination they move both in the positive x direction. So then we can write that combined mass mx my and with some velocity v. Now in terms of lambdas, what we can write? We can write that lambda of x, yeah, here it is mentioned as gamma, so let us write as gamma. So gamma of x will be h by mx vx. Gamma of y will be h by m by vy, and gamma, that is the final after collision, the final de Broglie wavelength, that will be h by the combined final momentum, and that is equal to this one. So mx plus my divided by, oh sorry, into v, and this can be written as h by this momentum value can be replaced by this value, so that will be mx vx minus m by vy. Now what I can do, if I take a reciprocal of this equation, then I will get 1 by gamma is equal to mx vx minus m by vy divided by h. This can be written as mx vx by h minus m by vy by h. Now this term is equal to 1 by gamma x. So 1 by gamma is equal to 1 by gamma x minus 1 by gamma y, and from this it will become gamma y minus gamma x by gamma x gamma y, and from that gamma is equal to gamma x gamma y divided by gamma y minus gamma x, or depending upon on which direction we are moving finally, it can be either gamma x minus gamma y. That's why we have modulus in option B. So option B will be the right answer here. Moving to the next one. Two particles move at right angle to each other. Their de Broglie wavelength are gamma 1 and gamma 2 respectively. The particles suffer perfectly in elastic collision. The de Broglie wavelength lambda of the final particles will be. So this is like the previous one question. Just now we have some additional information that they were moving perpendicular to each other. So we can say let's first particle was m1 and it is moving with velocity v1 in the x direction. Second particle is m2 and it is moving with velocity v2 in the positive y direction. So according to momentum conservation, we can write that m1 v1 of I component plus m2 v2 of j component should be equal to m1 plus m2, as perfectly inelastic collision is there, into some velocity v, which is the final velocity, which will have both x and y components. So again, we can write that lambda 1 will be equal to h by m1 v1, and lambda 2 will be equal to h by m2 v2, and lambda, that is the final, that will be equal to h by v modulus. Now how we will find out v modulus? Oh sorry, it, m combined mass, let me clear this one. Let me write it P modulus, not V modulus, P modulus, where P is the final momentum. Now this term is equal to final momentum, and if I calculate the magnitude, I can calculate from these two. So it will become H by under root m1 square v1 square plus m2 square v2 square. Now again take inverse of both of the sides and square. So 1 by lambda square will be equal to uh, m1 square v1 square plus m2 square v2 square by h square, and this can be written as 1 by lambda square is equal to m1 square v1 square by h square plus m2 square v2 square by h square, and this term is equal to 1 by lambda square, and second one is 1 by lambda 2 square. So 1 by lambda square is equal to 1 by lambda 1 square plus 1 by lambda 2 square. And that is option A for us. Moving ahead, a particle of mass m and charge q is accelerated by a potential difference 50 volt. Another particle of mass 4m or charge q is accelerated by potential difference of 2500 volt. The ratio of de Broglie wavelength we have to find out. So we know that work done W is basically Q times the potential applied, and this work done is equal to the energy acquired by the particle. And we know, we also know for the de Broglie wavelength, lambda is equal to h by p. Momentum can be written in terms of energy. It is 2m times e whole under root, and this energy can be substituted qv from this relation. So it becomes h by 2mqv. Now here h is universal constant, 2 is universal constant. Here mass and charges are different, I think. Here charge is same. Here charge q and here is also charge q. So we can say charge is also constant here. So basically lambda will be proportional to 1 by under root m times the potential. So if I take the ratio lambda a by lambda b, it will be under root m a v a divided by n b v b. So m a is m and potential difference is 50. Sorry, m into 50, and mb is 4m and potential difference is 2500. So this will get cancelled on 50, m gets cancelled, so this will be give us 200 under root lambda a by lambda b, and that is under root 2 under root, that can be written as 2 into 10 root 2, that can be written as, and root 2 is 1.41, so basically 14.1 is the required ratio. That is option C for us. So with this, we end this video here. Hopefully whatever we have covered here is helpful to you. Again, if you have any doubts or suggestion, you can put them in comment section. I will try to resolve them. And if you like this video, then share it, subscribe to our channel, like to support us financially, scan these QR codes and donate any amount. It will be highly helpful to us. With this, again, thanks for watching, and we will meet in next video.